If you have any doubt, you can straight away ask me your doubts, and then we can start the lecture. You can write your doubts in the chat box. Mhm. If you don't have any doubts in today's week or previous weeks, we can start today's class. Can you mute yourself? Okay. So let's start with today's class. So this is week 8. So this is week 8, and in week 8, before week 8, we had covered this conduction and forced convection. From now on, we will be covering the other modes of heat transfer, such as this. The one is another mode of convection, that is free convection, and later on we will be covering boiling and condensation. So in today's class, we will cover this free or natural convection and then see certain numericals related to it. And then we will study the boiling curve and then solve a few numericals related to it. So this is the prerequisite for free convection, that is the buoyancy force. So we know that any fluid or any object will fall under the effect of gravity, and this pressure variation within this fluid will be given by this equation, that is P equal to P naught rho g by z. And then we have this buoyancy force, that is basically the upward force due to the sum of pressure over an area. And in this object, we also have this gravitational force. So the net buoyancy force, we can write it as rho 2 Vg, where rho 2 is the density of this object or whatever fluid mass we are having. So basically, this shows that whenever we are having a material or objects of two different density, for example, if this is of density rho 1, this is of density rho 2, then different kind of forces such as gravitational force or buoyancy force will act on this whatever act on this system of object and the surrounding, due to which there will be motion of the object within the system. So the overall force, you can just equate it by this equation, whereas this is the buoyancy force and this is a total pressure acting on the object. So this just shows that whenever we are having this density difference, different forces come into account. So in what scenarios can we observe this density variation or density stratification? So the first one is due to the temperature difference. That is, if one fluid is at a different temperature and the same fluid, it has a higher temperature, then the density of the fluid at different temperatures will be different. Similarly, the concentration, if the concentration of the fluid or the concentration of substance or of the concentration of matter in the fluid is varying, then also the density will change. So if you just want to quantify this change with respect to temperature or concentration, you can just write this density at any given temperature concentration is equal to the initial density plus the rate of change of density with respect to temperature. So this is nothing but Taylor series expansion in two variables. In this course, we are only concerned with the temperature variation, that is the density change due to temperature. So we will neglect this concentration change. So this equation basically gives the density variation with respect to temperature. So this is basically, I'm showing that if we are having two liquids, so one is denser liquid and another is lighter liquid. So ideally the denser liquid should be below the lighter liquid. That is why the flow will be from the denser liquid to the lighter liquid. So lighter liquid will eventually move upward. That is stratification, basically different densities in different layer. Heavy fluid on top will continue to remain when there are no disturbances, and disturbances causes instability. Then if we just consider two different objects over here, that is two objects of the same density ρ2 and in density of the fluid of density ρ1, we have an object B of density ρ1. Then if we calculate the net force acting on both the objects A and B, it will be 0 for both the objects A as well as B. Since this objects A of density ρ2 is present in the fluid of density ρ2, the net force is 0. However, in the another case, if the object A that was of density ρ2 is present in a fluid of density ρ1 and vice versa, that is the object or the packet of density ρ2 is present in the fluid of density ρ1, then the net force won't be 0. So since the net force won't be 0, you can see the motion of the fluid from ρ2 to ρ1. That is what I said, that the fluid will move from the higher density fluid will be lower and lower density fluid will be on the top of the higher density fluid. So such a kind of motion, it sets up free or natural convection. And as discussed, this density difference can occur due to either concentration difference or temperature difference. So this is the main crux behind this cause of this free or natural convection, the density difference that can be caused due to temperature variation or the concentration difference. So there are different changes or different sources of this unstable stratification. That is, in what scenarios can we see this motion of the fluid or free convection? So the first one is a heat source immersed in a fluid. So for example, we are having a fluid at temperature some fixed 25 degrees Celsius, and then I have a heated wire going through this at temperature of 200 degrees Celsius. So this is basically a heat source that is immersed in a fluid. So due to this, there will be a density difference over here. Temperature is 250. So this part will start, the temperature will start rising and the density of the fluid, which is closer to the wire, will keep on decreasing and it will eventually move forward. So that is the heat source that is immersed in a fluid. Then the other example is the jet of hot fluid. And the third example is the flow of the fluid over the vertical walls. So these are all the sources of unstable stratification, that is whereby the disturbances can occur between two different kind of fluid layers. So yes, these are just the mathematical equations, that is momentum equations in boundary layers, that will help us to develop the Nusselt's number correlations for these free convections. So in case of forced convections, we develop many Nusselt's number correlation that helps us to find the convection heat transfer coefficient H bar. So similarly, for free convection, we perform all the similar exercises, and eventually we will be getting the Nusselt's number correlations that will be function of some dimensionless parameters. So while deriving those, we come across this important factor that you can call it as expansion factor or compressibility factor depending on this value. So that is basically -1 by rho del rho upon del t. And eventually, if you just write it in terms of dimensionless form, we obtain this dimensionless number, that is Grashoff's number. So it is nothing but it is essentially the square of Reynolds number. So if you just put it in the Nusselt's number correlation, that is, it is proportional to Reynolds number into Prandtl number, we can find this, that Nusselt's number is also proportional to Grashoff number, as well as Prandtl's number will remain the same. Then in the class, these are the slides from the class, whereby in order to quantify whether the given system is under forced convection, free convection, we can calculate this value, that is Grashoff's number upon square of Reynolds number. So if that value is less than 1, we can say that the forced convection dominates. When we say this value is very less than 1, that implies this Reynolds number is higher. When the Reynolds number is higher, it will mean that the velocity is playing a significant role, that's the forced convection is possible. And if this value is greater than 1, that implies Grashoff's number will be very higher. That implies that free convection will be more. And if it is equal to 1, then both forced convection as well as free convections are important. Similarly, if this value is infinity, that implies we are having a pure free convection. So yes, eventually we can write this Nusselt's number is a function of Reynolds number, Grashoff's number, and Prandtl's number. Then, depending on the type of flow, laminar flow or this turbulent flow, we can derive different kind of correlations. For example, in case of forced convection, we had derived these correlations of Nusselt's number, Reynolds number, Prandtl number. Similarly, in case of free convections, we can write this term, that is Nusselt's number will be proportional to the Grashoff's number raised to 1/4 and some function of the Prandtl's number. Then so in order to characterize this, whether we are transitioning from laminar to turbulent flow, for this free convection, we define this dimensionless number Rayleigh number, that is Grashoff's number into Prandtl number. And if that number is higher than 10⁹, that implies that we can say that we are transitioning into the turbulent flow. And if it is less than 10⁹, then we can say that we are having the laminar flow. So it's basically this Nusselt's number can be written in terms of Rayleigh number by these equations. It is for both this laminar flow as well as turbulent flow. Then we have these correlations that have been obtained by solving those momentum equations. So for laminar flow, we have this Nusselt's number correlation, and this says that if Reynolds number is very less, that is, if this terms become 0, then Nusselt's number will be a constant, and that value is basically 0.68. So yes, this was the basics of free convections. So there are different correlations that we need to use in order to find the heat transfer coefficient for free convections. So those correlations I will share once we are solving the questions. So now we can start with the boiling mode of heat transfer. So we define this boiling as liquid to vapor transition on a solid surface. So over here we need to have different phases, that is, we need to have a solid surface and the fluid over it. And once this solid surface is being heated, or it is at higher temperature, then we can say that the boiling occurs. Okay. So yes, this boiling curve is an important curve that can help us understand the phenomena of boiling. So this was illustrated by Nukiyama, whereby he had this a vessel in which water was kept at this 1 atmospheric pressure, and and there was this electrically heated wire. So this is an electrically heated wire, and the temperature of the wire or the heating was gradually increased. So basically, from 100 to 1000, that was the temperature was gradually increased, and the effect on the heat transfer rate was quantified by this boiling curve. So over here, we can see that this is the delta T term. That is nothing but the temperature of the surface of the wire upon the saturation temperature of water. That will be around 100 degrees Celsius at 1 atmospheric pressure. So if delta T is very close to 1, that is equal to 0. So this is basically 100 degrees Celsius, and this will become 110 degrees Celsius. So eventually, as we keep on increasing the temperature, we can see that the heat transfer rate will initially increase until a maximum point. Then it will gradually decrease to some lower point. So this point is known as Leidenfrost point, and then ultimately it will keep on increasing asymptotically as and when we increase the temperature. So there are different parts of this boiling curve. So the first part or the first segment is, we can write it as free convections. So in these free convections, the fluid temperature will approach the saturation, and the circulation will take place within the fluid vessel. And in this, you can see that as we keep on increasing the temperature, QS dash, that is the heat transfer rate, will keep on increasing. Then in the second phase, we have this nucleate. It is a part of nucleate boiling. So nucleate boil, so there can be surface irregularities or nucleates present, surface irregular presence on the surface, and due to those surface irregularities, bubbles will start form as we keep on increasing the temperature. So at the onset, there will be smaller bubbles and very isolated bubbles, and these bubbles will independently rise. So these are small bubbles, so they will just leave the surface of the wire or the surface or the solid surface, and eventually merge into, or eventually just go down into the fluid. Then eventually, and if we increase the temperature further, we can see that the constant jets or columns of these bubbles are formed. So now we don't have this isolated bubbles, we have this constant jet. So due to this constant jets, there is this vigorous motion in the fluid, due to which we can see that the heat transfer coefficient, or the heat transfer rate will rapidly rise. So eventually we will reach this critical heat flux. After this critical heat flux, we will be transitioning to the film boiling. So this region is the transition regime, whereby we reach this minimum point, that is the Leidenfrost point, whereby the heat transfer rate Q double dash is minimum in this boiling curve. So the last part is this film boiling, whereby if we keep on increasing the temperature beyond this Leidenfrost point, then the heat transfer rate will asymptotically keep on increasing. So in this, a layer or vapor of blanket will be always present. So over the surface, there will always be a blanket of this vapor. Okay, so that was all for the modes of boiling. Then there are these different correlations, that is the different formulas for the heat transfer rate in different regimes. So for example, if we are in this nucleate boiling regime, we can characterize the heat flux by these empirical equations. So these equations are derived empirically. So that is Q double dash is proportional to this viscosity, then HFG, then this term. So eventually, this is how we can quantify the boiling heat transfer rate in case of nucleate boiling. Similarly, the critical heat flux can be given by these equations. So one thing to note, important thing to note, is that this critical heat flux, that is Q double dash X, does not depend on this excess temperature. So this is not a function of delta T over here, whereas over here you can see that we are having this delta T. but it will strongly depend on the pressure through its dependence on surface tension and the vapor density. So you can see that this is the vapor density and this is the surface tension. So it will strongly depend on this surface tension as well as vapor density. That means it basically it is dependent on the pressure. Then we have this minimum heat flux at the Leidenfrost point. It is given by this equation. Again, it is dependent on the density of fluid as well as density of vapor and the surface tension. So for each of this mode, for film boiling also, we are having this correlation. So yes, that was all for the theory that was covered in the previous week. So now we can start solving the numericals. So meanwhile, if you have any doubt, you can just write it in chat box or unmute yourself and ask. So if not, we can start with this first question. You can try solving this question. You can try reading this question and I will just share the solution methodology with you and then we can solve the questions online. Just give me a minute, I will be back. So this is the first question and it is very straightforward, whereby we have been given that consider an object. We have been given that consider an object of characteristic length 0.01 meter and the situation for which the temperature difference is 30 degrees Celsius. Evaluating thermophysical properties at prescribed condition, determine the Rayleigh number for the following fluids. That is, we have been given the fluids of helium that is at 1 atmosphere and 400 Kelvin, and glycerin we have at 1 atmosphere and 285 Kelvin. So for this system, we have to calculate the Rayleigh number given these properties. So this is a very straightforward question whereby you just have to use the formulas corresponding to the Rayleigh number. So Rayleigh number, we write it as G beta delta T L cube upon mu alpha. So for helium, Rayleigh number of helium, you can write it as G will be 9.81, beta is 2.5 into 10 raised to minus 3, delta T is 30, length is 10 raised to minus 2 and its cube will become 10 raised to minus 6 upon mu is 199 into 10 raised to minus 6 into alpha is 295 into 10 raised to minus 6. So you can just cancel it out and this should become 9.5 into 1000 is equal to 73740 upon so this will come around 12.53. For helium, the Rayleigh number is 12.53, and again, this is less than 10 raised to 9, so we can say that we are having a laminar flow. Similarly, for glycerin, we can write the same as 9.81 into beta is 0.475, 10 raised to minus 3, delta T is 30, length cube is 10 raised to minus 6, and then mu is 2830 into 10 raised to minus 6 into alpha is 0.964 into 10 raised to minus 7. So this will get cancelled out, and we will be having so this will come around 512. So we found out that the Rayleigh number for helium for the given values of temperature and pressure was 12.53, and same for the Rayleigh number for glycerin for different values of this was 512, was around 512.41. So this is how you calculate the Rayleigh number. So using this Rayleigh number, you can characterize whether the flow will be laminar or turbulent. That will help us to choose the correct correlation in order to find the heat transfer coefficient. So let's see another question. Says we have to use this formula of Rayleigh number in order to calculate the Rayleigh number for different fluids at different temperature and pressure. So this is the second question, whereby I have also given the Nusselt's number correlations as a hint. So in this question, we have been given that a household oven door of 0.5 meter height and 0.7 meter width reaches an average surface temperature of 32 degrees Celsius during operation. Estimate the heat loss to the room with ambient air at 22 degrees Celsius if the door has an emissivity of 1 and the surroundings are also at 22 degrees Celsius. Determine the ratio of heat loss by free convection relative to that of radiation. So in this question, first we have to find the total heat loss to the room that is at an ambient temperature of 22 degrees Celsius, and it will be due to this radiation as well as free convection. And in the second part, we have been asked to find the ratio of that heat loss due to free convection relative to that of radiation. And in the hints, we have been given the Nusselt's number correlations for the given system, and also the heat loss by radiation is given by the Stefan-Boltzmann law. So in order to solve this, first you need to find this heat transfer coefficient. So once you have this heat transfer coefficient, you can calculate the heat loss due to convection, and for the heat loss due to radiation will straight away given by this equation, and then you can add both the terms in order to find the total heat loss. Similarly, in order to find the ratio, you can just take the ratio of both the terms. But before using this equation, first we need to find this Rayleigh number that needs to be put over here. So once we calculate the Rayleigh number, we put it over here, and then from this equation we calculate the h bar, that is the heat transfer coefficient of convection, and from that we can find the convective heat transfer rate as Q equal to HA delta T, and the radiative rate is given by this equation. So yes, let's try solving this question. This is question number 2. So just to get an idea of the sketch, we have been given an oven door of height as 0.5 meter and width as 0.7 meter, and this reaches an average temperature of 32 degrees Celsius. The ambient air is at 22 degrees Celsius. So due to this, there will be Q convection as well as Q radiation, and Q total, that is what we have to find. It will be simply summation of Q convection plus Q radiation. So this convection will be free convection since we haven't been given the velocity at which the air is moving. So that implies that we can assume that we are having a free convection over here. So yes, so in order to solve, let's just first calculate the Rayleigh number. So Rayleigh number is given by G beta delta T L cube upon mu alpha. So let's just put all those values. It will be 9.81 and beta is 3.33 into 10 raised to minus 3. Then delta T will become 32 minus 22, that is 10. So for convection, you need to treat this vertical height as the length, because for convection you always need to consider this vertical height as the length, that is 0.5 meter into Q upon mu is 15.89 into 10 raised to minus 6. The alpha is 22.5 into 10 raised to minus 6. So this will be coming as 9.81 is 40834 to 10 raised to 6. 15.8. So the value of Rayleigh number comes around 1.14 into 10 raised to 8. So this implies that we are not in the turbulent flow, that is we are in the laminar flow or laminar flow. So for that we have been given this convection, free convection correlations. So we need to use that in order to find this H bar. So first let us just find the value of Rayleigh number raised to 1 by 6. It will be this will come out 22.02. Then we can find this value also, that is 0.492 upon Prandtl number raised to 9 by 16, as Prandtl number we have been given as 0.707. You need to be very careful about this calculation since we are having these powers and also very different formulas. 0.707 raised to 9 divided by 16 is equal to 0.8155. Now we can replace these powers in these equations, so that will give us Nusselt's number is equal to 0.825 plus 0.387 into Rayleigh number is 22.02 upon 1 plus, we found out this 0.8155 raised to 8 by 27 whole square. So now we can further simplify this as so this will come around 0.825 plus 7.141 whole square comes around 7.96 whole square. So it comes around 63.46. So Nusselt's number for the given system is around 63.46. So from that we need to calculate this H bar, that is the heat transfer coefficient, that is HL upon K. So H will become 63.46 into value of K is 0.0263. So this value comes around 3.338. So the value of heat transfer coefficient, that is the value of convective heat transfer coefficient, is 3.338. And now in order to find the convective heat transfer rate, this Q convection, we can write this as HA Ts minus T infinity. So the area is 0.5 into 0.7 and delta T was around 10. So this will come around 3.338 into 0.5 into 0.7 into 10. So the value of the Q convection will come out 11.69. So now we also need to find the Q radiation. So Q radiation is given by the Stefan-Boltzmann law that states that epsilon sigma A into T raised to 4 of the surface minus T raised to 4 of surrounding. Epsilon, I think we were given as 1, emissivity is 1, and Stefan-Boltzmann constant is, we haven't been given, but it is around 5.67 into 10 raised to 8, I think. So you can put that value, and the value of area is around 0.7 into 0.5. And then, so 1 into sigma into 0.35 into temperature of surface is 32. That is 273 plus 32 raised to 4 minus of 273 plus 22 raised to 4. So you can just calculate this, and the value of Q radiation will be around 21.44. So yes, the ratio that was asked was convective to radiative, that is Q convection upon Q radiation. So it will come around 11.69 upon 21.44. So this comes around approximately 0.5. So yes, you can write this as 0.55. So the ratio of heat transfer due to free convection and that due to radiation is around 0.55. So that is what was asked in this question. This is the solution. You can just take a quick look on it, on how we solved, and then we can move on to the third question. Now let's move on to the next question. So we will skip this question number 3 since it has been asked in your assignments. But we can move on to this question number 4. So let's read the question number 4. We have been given that estimate power required to maintain a brass plate at delta T is equal to 15 degrees Celsius while boiling saturated water at 1 atmosphere, and CSF is 0.06 and N equal to 1. So in this case, we are having this boiling. In earlier questions, we were solving related to the free convection, but now we are having this boiling mode of heat transfer. So for that boiling mode of heat transfer, in order to maintain a brass plate at 15 degrees Celsius, we had to calculate the estimated power required. And we have been given different properties of the water and as well as vapor at saturation temperature and pressure. So the overall heat transfer rate, that is Q double dash, we saw it from this. So for example, since delta T we were given as 15 degrees Celsius. So yes, over here you can see that delta T is 15 degrees Celsius. That implies that in the boiling curve, we are over here, that is a nucleate boiling. And for this nucleate boiling, we have been given this formula. So we need to use this formula. So this proportionality constant we have been given. So ultimately by using this formula, we can calculate the heat transfer rate, that is basically the power required. So let's solve this further. This is question number 4. So again, this is a very straightforward question whereby you straight have to use the formula of the power for this nucleate boiling. But for that, first you need to identify that since delta T was 15 degrees Celsius, that means that there will be nucleate boiling. And for this nucleate boiling, have been we need to use the heat. We need to use that equation that was provided. That is Q double dash S as mu L HFG then G into rho L minus rho V upon sigma 1/2 into Cp of liquid, the excess temperature delta Te, then this constant CSF, HFG, Prandtl number of liquid raised to n and the whole cube. So using this equation, you can put all those values and you can try finding the value of power. So let's try to solve this. So the viscosity of the liquid, that is mu L, is given as 279 into 10 raised to minus 6. Then these terms corresponding to this buoyancy are given as 9.81 into density of liquid is 957.9 minus of 0.596 upon sigma surface tension is given as 58.9 into 10 raised to minus 3 1/2 Cp of liquid is 4217, delta Te is 15 upon CSF is this constant of 0.006. HFG we were given somewhere. This is 2257. Prandtl number is 1.76. The value of n is 1 raised to cube. So let's calculate this. So 957.3 into 9.81 divided by 9,000. And 400. And then we have this 4217 15 divided by 0.06 7 6. This comes around 1.86 into 10 raised to 10. So wait a minute. So I might have made a mistake somewhere. So the value of CPL is 4217, delta T is 15, CSF is 0.006. HFG we have been given, Prandtl number is 1.76. You can unmute yourself or write it in chat box. But you just need to simplify this and it will come. Mm-hmm. Mm-hmm. No, so that we have been okay. Yes, here we have this correct. Uh-huh. Correct, correct. Mm-hmm. Mm-hmm. Uh-huh. Correct. You can just multiply it by 10 raised to 3. So if you just do it, so you can just simplify this and the value I have the solution as. So the solution comes around 4.70 megawatt per meter square. So you just need to be very careful about replacing all those values in these large formulas whenever we are using. So in this question, in order to find the power, the heat transfer rate, you had to first find whether the in which regime the fluid in which regime of boiling were we present, and then corresponding to those correlations, we can find the power. But again, you need to be careful about putting all those values. So if we just put all those values correct, for example, it should be 10 raised to 3, and if we simplify it, it should come around this 4.7 megawatt per meter square. That is the final answer that I am having over here. So you can replace all those values and it should eventually come to around 4.7 megawatt per meter square. So I have this Excel sheet over here. So whereby if I just replace all those values, it comes around 4.7 into 10 raised to 6 watt per meter square. That will be eventually 470 megawatt, 4.7 megawatt per meter square. So yes, if we now let's take a look on the next question. That is question number 5. After this, we have 3 more questions. So in this question, we have been given that a steel bar of 20 mm in diameter and 200 mm long with emissivity of 0.9 is removed from a furnace at 455 degrees Celsius and suddenly submerged horizontally in a water bath under atmospheric pressure. Estimate the initial heat transfer rate from the bar. Consider this sigma, that is Stefan Boltzmann constant, we have been given, then C as 0.62, and the water temperature we have been given as the saturation temperature as 100 degrees Celsius, and that we have been given the density of water as well as this HFG. Similarly, for vapor, we have been given this properties at the temperature of mean of this 100 as well as 455 degrees Celsius, that is 550 Kelvin. All these properties are given. And the total heat transfer coefficient of the system can be obtained by solving this nonlinear equation. So from that is basically a function of H convection upon H radiation. And if this radiation term is less as compared to the convection, you can just simplify this as H convection plus 3 by times of H radiation. And also this, in order to account for this HFG for different temperature other than the saturation temperature, you can use this straightaway linear equation in order to find this HFG at this given temperature, at the surface temperature. So again, this H radiation, it is the convective heat transfer rate, the convective heat transfer coefficient due to the radiation. So that you can, in order to find that, you can just equate this as H radiation A times Ts minus T saturation. And this you can equate it to the radiation heat transfer, actual radiation heat transfer, that is epsilon sigma A upon Ts raised to 4 minus T saturation raised to 4. A will get cancelled, and then you can take this term over in the denominator, so that will give you the convective heat transfer, the radiative heat transfer coefficient H rad. So yes, let's try solving this question. Again, in this question, we will be requiring the Nusselt's number correlations that I will share in order. So in order to find this H convection, you need to know the Nusselt's number correlations that I will be sharing. So let's try to solve. So as discussed, first the heat transfer rate is H bar A into Ts minus T saturation, but we don't know this H bar, that is due to first due to convections. So for that we can write this Nusselt's number as H D upon K, and then we have to use this correlation, Nusselt's number correlations, that is Nusselt's number is C times this parameter of, I will just write the equation over here, G into rho L minus rho V into H dash HFG d cube upon gamma V. This is the dV kV into delta T, that is excess temperature, raised to 1 by 4. So these equations will be provided whenever you have to solve such kind of questions. So from this, you can replace all those values in order to find this value of heat transfer coefficient. But first we need to find this HFG at the given temperature. So we have been given this HFG at 100 degrees Celsius, but we need to find this HFG at the saturation temperature. So in order to do that, you can just use this equation over here, and it will come around H dash Fg is equal to 2257 kilojoule plus 0.8 into Cp. V is around 1.997 kilojoule. Temperature was, I think, 455. So this term will come around 567. So 567 plus 2257 will give you around 2824. So this 2824 you can replace over here. So let's just do it over here only. So the value of C we have been given as 0.62. Then G is value of C is 0.62. Value of G is 9.81. rho V we have been given, rho L we have been given, so that we can just write it as approximately 957. H dash Fg we have been given in kilojoule as 2257 to cube, and then diameter we have been given as 20 mm, so that is 20 cube into 10 raised to minus 3 minus 6 minus 9 upon VBS 47.04 into 10 raised to minus 6 kV is this value 0.0379 into delta TE, that is the excess temperature is 100 minus 455, so it will be 355. So you can again try calculating it. 9.81 into 957 2257. So you will be getting some denominator, and eventually the value of Nusselt's number you calculate should come around 83.88. So that is the Nusselt's number for the given system that we obtained, and from this Nusselt's number you need to calculate the value of heat transfer coefficient H. So it will be 83.88 into K by D. So this value of heat transfer coefficient will come around 158.95. So this is the heat transfer coefficient due to convection. Similarly, we need to find the heat transfer coefficient due to radiation. So that, as I discussed, it was epsilon sigma Ts raised to 4 minus of T surrounding raised to 4 on Ts minus T saturation. This should be saturation. So this will give you the value of epsilon is I think 0.9. Into 5.6. 8. Temperature of the surface is 455. So this H radiation will come around 37.59 watt per meter square Kelvin. So now we have this H radiation as 37.59 as well as H convection was around 158.95. So from the over here you can see that H radiation is less than H convection. That is from the given hints, that is H radiation is less than H convection. So we can use this thumb rule. So the H bar will become H convection plus 3/4 of H bar radiation. So the overall heat transfer coefficient from this, you can calculate it as 158.95 plus 3/4, 37.59. This will come around 28.19 plus 158.95. So the overall heat transfer coefficient for the system of convection as well as radiation will become 187.14. Let me just check that. Yes. And then you have been asked to find the overall heat transfer rate. So QS, let me just check what you have been asked to find. So yes, you have been asked to find the heat transfer rate. So it will become HA delta T. So you can use this H over here, 187.14 into pi into diameter is 20 mm and 200 mm is the length. In meter it will be 10 raised to minus 6. Delta T is 455 minus 100. So this will come around 834.85. So the overall heat transfer is 834.85 watt. That is what was asked in the question. So for the given system whereby steel bar was immersed in a fluid, that is water, for the given system, we had to find the heat transfer rate from the bar. So that we calculated by using this methodology. So you can take a quick look on that and then we can move to the next question. So let's take a look on this question number 6. So in this question, we have been given that we have been asked that what is the maximum allowable uniform heat flux that may be imposed at a wall heating panel 1 meter high if the maximum temperature is not to exceed 37 degrees Celsius when the ambient air temperature is 25 degrees Celsius. Then we have been given the properties at 37 degrees Celsius. And then we have been given the hint that is for an isothermal plate. The temperature difference at any x is given in terms of this temperature difference at L by 2, that is at the midpoint by this equation. And then for the laminar flow, we have been given this Nusselt's number correlation that will help us to find the heat transfer coefficient. And from this heat transfer coefficient, we can find the maximum allowable heat flux at this one, if the height is 1 meter. So for that, one thing is we need to find this delta Tx, that is when L length is equal to 1 meter, that is delta T1 we need to find, as well as we need to find this H bar. So once we have that, we can use this Q equal to H delta T in order to find the heat transfer rate, in order to find the heat flux. So yes, let's try solving this. So as discussed, so if you have to draw the diagram, we have been given this wall, which is basically 1 meter height, and we are imposing a heat flux that is Q double dash S, and this is our direction of X, that is for the vertical, right? And the temperature will be maximum at the top surface, that is given as 37 degrees Celsius, and over here we are having air at 25 degrees Celsius. So first we need to find this delta T, the maximum possible delta T that is present at x equal to 1. So in order to find that, you can just write this as delta T x we have been given as Tx minus T infinity is 1.15 x by L 1 by 5 delta T L by 2. But first we need to find this delta T L by 2. So for that, if x equal to 1, then we already have this delta T as 37. The maximum temperature is 37, so it will become 37 minus 25, 1.15, since x equal to L, that's 1 meter, so this term will become 1, and from that we can get the temperature difference at this point. this delta T L by 2. This is delta T L by 2 is equal to this is 37. So delta T at L by 2 is 10.14 degrees Celsius. Or you can also write the temperature at L by 2 will be this 25 degrees Celsius plus 10.4 degrees Celsius. So this will come around 34.4 degrees Celsius. So this is, we have find the temperature at this midpoint. So all those parameters, that is Rayleigh number as well as this Rayleigh number, we will be calculating at this midpoint, that is L by 2. For that is why we need to calculate this delta L by 2. Since this Rayleigh number will be varying with respect to delta T, and in this given question this delta T is varying with respect to x, we can just take an approximation that we can find the value of delta T at the midpoint and then use that delta T for calculating the Rayleigh number that needs to be used over here. So yes, the formula for Rayleigh number was G beta L cube upon delta T L. But since this delta T is varying with respect to x, you can just write delta T L by 2 upon mu alpha. Then you can replace the values as 9.81 into value of we haven't been, I think, given the value of beta. So we haven't been given the value of beta. Let me just check. So I don't have the value of beta right now over here. So I'll just share the solution methodology. So if we just put the value of beta as over here, then the value of length you can put as L by, you can straight away put the value of length as whatever 1 meter we have been given, then delta L by 2 we calculated, delta T L by 2 we calculated, mu and alpha we have been given. Did we given beta over here? No, so we haven't been given beta. So basically this will give some value of Rayleigh number, and that Rayleigh number you can put over here. Then again you have to do similar exercise where you have to find this value of h bar, and then from h bar you can find the heat transfer rate, that is heat flux, that is H delta T. Since we haven't been given the value of beta and not having the value of beta in this problem set, so we can just skip solving this question numerically. We need the value of beta in order to calculate the value of Rayleigh number. So now let's move on to the next question. That is question number 7. So I think in the previous question, you can use the value of beta as 1 upon TF, and TF is nothing but you can just calculate it as T infinity So in this question, we weren't given value of beta, but the value of beta is 1 upon t, where t is, I think we calculated TL by 2 plus T ambient air by 2. TL by 2 we had calculated as 35.4 plus T ambient was 25 plus 2. So you can just calculate T over here and take the inverse of that and then find the value of beta. That will help you to find the value of Rayleigh number. So you can calculate that on your own. Let's see the next question. So in this question, we have been given that a circular grill of diameter 0.25 meter and emissivity 0.9 is maintained at a constant surface temperature of 130 degrees Celsius. What is the electrical power required when the room air and surroundings are at 24 degrees Celsius? The relevant assumptions are given, and then we have been given the properties of air at the film temperature, that is 350 Kelvin. And all those parameters we have been given, and then basically we have been also provided this heat transfer correlations, which is the Nusselt's number correlations, and we have been also given the radiative heat flux. So overall, again, we have been asked to find the electrical power. So that will be a summation of convective power as well as the radiative power, that is the heat transfer rate due to convection as well as radiation. So Q we have been asked to find, and it will be the summation of Q convection plus Q radiation. Q convection, we know it is H convection upon area surface upon Ts minus T infinity. Similarly, Q radiation, that is the exchange, we can write it as plus epsilon A S Ts raised to 4 minus T raised to 4 surrounding. There will be sigma. So for that, we first need to find this value of convective heat transfer coefficient. So very similar to the previous questions, we need to use this equation. For that, we need to find the Rayleigh number. So Rayleigh number is given as G beta Ts minus T infinity upon Lc cube upon mu alpha. So the value of beta we can calculate by this 1 upon Tf. So this, if we just put the values, it will be 9.81 into 1 upon Tf is 350 Kelvin. Ts minus T50 Tf. Ts minus Tf is 106. Then yes, this value of Lc we haven't been given so far, but we haven't given this is a horizontal disk. So the characteristic length for any system, we know that it is the ratio of area upon perimeter. The area of the cross section, the area of circle is pi d square upon the perimeter is 2 pi r or pi d. The area is pi by 4 d square, that is pi r square. So the characteristic length for this circular disc will be d by 4. So this Lc you need to use as d by 4, that is 0.25 upon 4 whole cube upon mu is 20.9 into 10 raised to minus 6 into alpha is 29.9 into 10 raised to minus 6. So you can try calculating the Rayleigh number, and Rayleigh number will eventually come within this range of 10 raised to 4 to 10 raised to 7. So the exact value will be around 1.158 into 10 raised to 6. So from this Rayleigh number, you need to calculate the Nusselt's number. So Nusselt's number will come. I don't have the value of Nusselt's number, but I have the value of heat transfer coefficient. So this will be h bar L upon K. So the value of heat transfer coefficient due to convection will be this term into K is 0.03. Will be calculated as D by 4. So if you calculate the value of heat transfer coefficient will come around 8.50 watt per meter square Kelvin. So eventually you need to put this value of heat transfer coefficient over here. Area we are having, Ts minus T infinity we are having, and this radiation we had calculated in the previous questions. So this is very similar to that question. So ultimately you can just put all those values in this equation and find the overall heat transfer, the overall heat transfer rate, or the overall heat energy. So basically this Q convection should come around 44.2 watt. Q radiation will come around 46.0 watt. So the overall heat transfer will be 90.2 watt. So this you can try calculating on your own. So this is the model solution. So the only thing new in this question was we were given this circular disc, and for this circular disc, the value of characteristic length you need to calculate by the ratio of area upon perimeter. Rest all we have this usual procedure whereby you have to calculate the Rayleigh number and then use Nusselt's number correlations in order to find the heat transfer coefficient. And then from the heat transfer coefficient, you can calculate the heat transfer due to convection and also calculate the heat transfer due to radiation, and then sum both in order to find the overall heat transfer. So this is the last question of the day. So we have been given estimate the power required to maintain the brass plate at delta TE is equal to 15 degrees Celsius while boiling the saturated water at 1 atmosphere. What is the power requirement if the water is pressurized to 10 atmosphere? And what is the power using the following assumptions used for nucleate boiling and delta T of 15 degrees Celsius for both the pressure levels? So for the given system, we had to calculate the power required at 1 atmosphere as well as the power required at 10 atmosphere. And for both this power, that is 1 atmosphere as well as 10 atmosphere, we have been given the density of the vapor as well as the other parameters that we have been given. So these parameters are for 10 atmosphere. These parameters are for 1 atmosphere. And then we have been given this power equation, that is the heat transfer rate, given by this Rosanov correlations. So this question is almost similar to the previous question that we solved. So in which question we saw this? So yes, this is very similar to the question number 4, but here we also have to find the value of delta T at 10 atmosphere. Rest all parameters and as well as delta T same as question number 4. So you can try solving this question on your own. But the only thing to note was the if you just look at the solution at 1 atmosphere, the power requirement is 4.7 megawatt, as well as is higher at higher pressure, the power requirement will become higher, that is 23.8 megawatt. That is at higher pressure. In order to boil the water by an excess of 15 degrees Celsius, the power requirement will again increase from 4.7, it will increase to 23.8 megawatt per meter square. So if you need to boil water at higher pressure, you need to provide this higher power. That was the meaning to that was demonstrated in this question. So yes, those were all the questions related to boiling as well as free convections. So the main thing in this question is you need to remember few of these core formulas and the other Nusselt number correlations that will be provided, and just most of them is finding the overall heat transfer rate or heat flux or the power by finding the Rayleigh number, and then depending on the flow regime you need to use the Nusselt number correlation, and then eventually you can obtain the heat transfer coefficient from that and then find the value of power. Since that was all for today's class, I will be here until 9 p.m. So if you have any doubt, you can just ask me. The solutions of all the assignments are being regularly posted on NPTEL, and the slides are also available on that NPTEL link as well as recording. So you can, if you want, you can just go through the slides and solve the questions if you want. So yes, you can ask me the doubts if you have in previous assignments or current assignment, but we won't be solving the questions of the current assignment, but most of the questions are similar to the ones that I have discussed. If you don't have any doubt, we can end today's session. I will be here for a couple of minutes. You can just ask your doubts if you have any. Let's end today's session.